The final topic in the unit of electricity and magnetism is called simply electromagnetism, and is the place where we finally see that electric fields, electric currents, magnets, and magnetic fields are all connected to each other. This particular concept is kind of hard to cover in an introductory level physics class because there's a lot of math. Instead, we're going to take advantage of that excellent simulation software found in the website called PhET. For the next minute or so, you're going to see me playing around with one of the apps on the PhET website. It's not the most powerful one, and it's not the one that's designed to be used with the worksheet that I gave you in class. It's one that is friendly for my phone, however, and since I'm recording and editing all of this video on my phone, it's the one I'm going to use. If you move the north pole of a magnet towards a coil, or if you move the coil towards the north pole of a magnet, and you have an ammeter connected to the coil, then you will register a positive current in that ammeter. If, on the other hand, you move the south pole of the magnet towards the coil, or you move the coil towards the south pole of a stationary magnet, you find that the ammeter records a negative current, a current in the opposite direction. The obvious conclusion, of course, is that any sort of motion between a magnet and a coil causes an electric current. We would say that this induces an electric current, and in general, this is called electromagnetic induction. And this is why this unit is called electromagnetism. Back when we were learning about currents and resistors and circuits and voltage and so on, you saw that if you hooked up a battery to a wire, then a compass needle nearby would move. So electricity was causing magnetic effects. Now you're seeing essentially the reverse, that moving magnets can cause electric currents to appear. And this is why you often see the phrase electromagnetism or electromagnetic, because these things are two sides of the same coin. from the other simulations that you've done in the virtual lab on PhET, or from a couple of demonstrations I did in class on the last day before you left, you'll see that if you hook a current up to a coil, then it'll cause any magnets nearby to move. Of course, this is just the reverse of what was described over here. What was described over here might be called a generator, whereas what happens over here might be called an electric motor. The key is that these two effects aren't really any different. They just are the same thing in reverse order. It's worth asking the question, why should we care about any of this stuff? And in fact, I'm sure some of you have been asking yourself that question ever since you started physics. But here I think is a place where you can see physics show up in real life all over the place. First of all, just about every power plant, except for maybe a solar power plant, works on this exact principle. In coal and in nuclear power plants, basically you're using either burning coal or burning oil or burning natural gas. In the case of nuclear power, you're using splitting heavy atoms. And what that's doing is causing a vat of water to start to heat up and become steam. That steam rises and passes through a turbine and causes the turbine to spin. If the thing that is spinning is connected to a coil, and that coil is moving inside a magnetic field, then you can generate a current in that coil. And that's basically how all modern electricity generation works. In the case of all electric motors, and these show up not just in children's toys, but also in all automobiles, all boats, etc., what you've got going on is you've got a battery connected to a coil. The coil is often called the starter solenoid or just the starter. And when that coil has an electric current running through it, then you can cause motion. In this case, you have a shaft that spins, and that thing connects to the main engine, which starts spinning, and that gets the whole gasoline engine process started. In general, you can say that the magnetic field is acting as a transducer. The transduction that's taking place is between kinetic and electrical energy. In the case of a generator, you have motion that eventually causes a current. In the case of a motor, you have a current that eventually causes motion. So you have transduction taking place between, and that shows up all over the place in modern society. If you go back into PhET and play around with the simulations that involve coils and batteries and light bulbs that are lighting up, you can see that there's a few ways that you can cause the light to light up brighter. One is simply to increase the amount of motion. Another is to increase the number of coils inside the coil of wire. Every time you get an extra turn of wire in your solenoid inside your coil, you amplify the effect. And finally, of course, a stronger magnet. On the final exam, you'll see a problem that involves asking you how to make an electromagnetic induction effect stronger, either faster motion, more coils, or a stronger magnet. I forget which one the question asks. Well, that about does it for the final unit of electromagnetism. What I'll do as soon as I can is start getting ready for the next unit that you guys would have studied if you were in class. That unit would start roughly in 2 weeks. and would be optics and waves.